Everyone hear me okay? Let me tell you all a little story. So last night I was checking into my hotel at the Cambria right here around the corner, and I encountered what I think was the tallest human being I've ever seen in my entire life. When I looked at him, my thought was, this guy's got to be at least 6'10". I noticed he was wearing an Ole Miss jacket, and it turns out Ole Miss was in town for a little game last night against the Gamecocks. Now, out of curiosity, I had to look up the roster and see just how tall this guy was. I was off by a few inches. He was 7'2". So, never know who you'll run into at these hotels getting on the elevator. So let's talk about this emerging technology. So high polymer is not necessarily a new thing, but I remember when the test section was built at NCAD in 2009, and back then it was mostly just about research. Okay, now there's become a pretty significant demand for information and research and even implementation of these highly modified binders since that time. It's really kind of exploded. So as we kind of move through this topic, first let's kind of talk about why do we even modify asphalt in general. So the primary concern, of course, is the high temperature range of the binder where we experience rutting. Okay, so if we just look at the basic PG grading system, we use a number that's supposed to represent the climate in a given region, and that's supposed to ensure that this binder isn't going to liquefy and cause any rutting issues just based on the climate. But the other factors that we have to consider are the loading conditions, the magnitude of the loads that we're dealing with, as well as the speed of the loading. So slow loads are a more critical condition for rutting than fast-moving loads. Okay? And a stationary load is, of course, the most critical condition that you can have for rutting. So the way we deal with that in the PG grading system is something that we call grade bumping. Okay? So we take the PG grade that's appropriate for a given region, and we can bump that grade 1 time or 2 times or 3 times in 6-degree increments. And this is supposed to give us protection against the environment, as well as the extremity of the traffic loading, as well as the speed of the traffic loading. Okay, so this is the way the original PG system was made up. So of course, what I'm trying to say is that if you increase the stiffness of the PG grade, without a doubt, that will reduce the deformation in the surface. Okay, that's a fact. However, that doesn't tell the full story. And if you look at these pictures in the upper right-hand corner, we have a case study that's been highly referenced, and it's just a great example of why we put polymers in asphalt. So you can have a PG64, which is a common grade. I believe that's the appropriate grade for South Carolina, and a PG67 minus 22. So if you're just looking at stiffness, without a doubt, the PG64 minus 22 should deform more than the PG67 minus 22. However, in this case study, you can see that the PG67 minus 22 experienced 15 millimeters of rutting, despite being stiffer, whereas the PG64 minus 22 experienced no rutting. Now, this was a modified asphalt, and what the polymer is doing is creating a string-like network inside of the asphalt, kind of like a web, if you will. And so it creates a lot of elasticity in that binder. So when it deforms, even if it deforms more, it has the capability of returning back to its original position. Okay? That's the basic reason why we modify binders. Now, when you get that extra elasticity, it also leads to improvements in the intermediate and low temperature range as well, because this is a more flexible binder. Now, we're interested in these high temperature properties such as softening point and stiffness, but we also need these properties that measure recovery. Okay, so we came out with another specification, AASHTO M332, and you may have heard of the massacre test, the MSCR. This allows us to measure the ability of an asphalt to recover. Okay, so you can measure something like percent recovery using the DSR. You can measure elastic recovery. Okay, so these tell us a little more about how that binder can respond to different loads. So overall, we tend to see a wider useful temperature interval. This is the difference between the high temperature grade and the low temperature grade of a binder, and that's generally considered to be a good thing as that range is getting wider. Some studies have shown that you can get up to 10 times the resistance to the load-initiated distresses, rutting and fatigue cracking primarily. Now, the benefits of using polymer is going to be highly dependent on the type as well as the dosage of polymer that's utilized. And that itself is going to be based on a lot of factors related to the binder chemistry as well as the viscosity of the binder and different handling factors. So this is kind of a demonstration that's done to show what I'm trying to communicate about the ability of the binder to return to its original form. So if you stretch out a binder that contains no polymer modification, it's not likely to return at all to its original form. It's going to stay deformed after it's separated. However, if you take a specimen that's been modified with polymer, it's very likely to return very close to its original condition. So, not here to talk a whole lot about research of polymer modified asphalt, although I just want to say that it has been heavily researched. In fact, the Asphalt Institute had a groundbreaking study in 2005 that was looking at the life extension benefits of polymer modified asphalt using data from all across the U.S. and various climates. So it's been proven to add or enhance the rutting resistance, the fatigue resistance, and the overall life of an asphalt binder. So what we're here to talk about, high polymer. So what makes an asphalt high polymer? Okay, there's a lot of confusion around this, and it's probably due to the fact that different states use different definitions. And so let's kind of talk through this. When we talk about polymer, obviously there are different types of polymers. You have the SB family, SBS, SB, SBR. You have terpolymers, trade name Elvaloy. You might have heard of those. When I'm talking about polymer modification, I'm mostly thinking of SBS. I think that's the most common polymer that we use in the asphalt paving industry. So as far as high polymer, if you're looking at a dosage basis, a standard dosage of polymer would be in this kind of 2.5 to 3.5% range. That would take a PG64 or PG67 and it would make it into a PG76 minus 22. Okay, that's about a 2.5 to 3.5% dosage of an SBS type of polymer that's been cross-linked. For high polymer, this is the broad category that kind of encapsulates all of the different technologies, okay? So if we're saying high polymer, we're talking about everything. If you see the term high Ma with that trademark symbol, that is a trademarked product. That is one company, one product, okay? Now that particular product is exclusively used at a dosage greater than 7%, okay? You're typically seeing that around 7 to 7.5% dosages. The HP does include that product, but if I were to just say that the entire broad category of high polymer is probably above 5%, would cover almost all the technologies that I've seen. Now the final properties, of course, are going to be based on the dosage or the loading rate of that polymer, as well as the neat asphalt grade. So in other words, if we start with a PG64 and we add a certain amount of polymer, it's going to get to a higher grade than if we start with a PG52 or a PG58 and add the same amount of polymer. So the final grade can vary. The way that I recommend looking at high polymer is based on a set of properties, as I mentioned. So measuring something like elastic recovery or MSCR percent recovery, okay? If a DOT is looking to get a particular value, a certain amount of elasticity out of that binder, in my opinion, that's the best way to do it without specifying any polymer dosages, especially considering the wide variety of different polymers that we have and the different technologies. Now I want to point out this S-shaped curve on the bottom. This kind of shows what happens to the asphalt polymer network at different loading rates. Where we're typically living is down here in this 2.5 to 3.5% range on the bottom. And at this point, it's really, asphalt is the dominant phase. And the polymer network is within the asphalt, but asphalt is still the dominant phase. And as you move up this S-shaped curve and get above about 6% on the polymer dosage, there's a transition that takes place where, although that polymer is only there at 6% plus, the polymer begins to become the dominant phase. And you almost have an asphalt extended polymer rather than a polymer extended asphalt. So although it's just a dosage, it actually makes a huge difference in the type of material that you're dealing with. Much more elastic material, much different behavior out of that material. So This is a state of the practice document that was published in 2021, and a lot of the information that I have is from this document. If this is something that you're digging into, I highly recommend this. My colleague at the Asphalt Institute, Johnny Habouche, is one of the leading researchers on this topic, and of course I consulted with him before I came to give this talk. But this is a great resource. Here's a map that I'm sure none of you have ever seen because this hasn't been published yet. I was given permission to show this map. This will be published in a couple of weeks through an FHWA tech brief. But what this map shows is the different agencies that have adopted this technology and developed a specification for this technology. And it's broken into kind of the green color that you see and the red stripes. And that's just looking at the type of specification that they've used, whether AASHTO M320, which is that basic PG grade that relies on grade bumping, or the AASHTO M332, which instead of grade bumping, maintains the true grade and adds a letter such as E to say that it's appropriate for the environment, but also can handle an extreme traffic level. Okay, so just kind of differentiates it based on the specification. You also see these stars on the map. These are the different states where Asphalt Institute, through this cooperative agreement with the FHWA, has done an in-depth survey and discussions with these departments of transportation to learn as much as they can about the use of high polymer. I'm not going to talk about all of these today during my time, but I will talk about a few of these states with stars on them. So kind of the genesis of high polymer was that you had these really extreme conditions. So you had cases where, I would describe it this way, if you're dealing with such an extreme condition that you're considering moving to concrete pavements, okay, this is kind of the last resort. Okay, can you stop the rutting before it gets converted to a concrete pavement? And we've seen situations where, at intersections, heavy loads, that you're actually, you just can't resist the rutting that's happening. Okay, so initially high polymer was for those extreme applications. However, we've really seen that expanded into many different applications in more recent years. In fact, you've got, based on the previous map, you've got 29 states that have adopted high polymer and implemented specifications. And you've got the state of New Jersey, which I believe has the highest usage that I have seen, with 5 million mixed tons have been placed. And you've got many other states that are in the hundreds of thousands and increasing every day. So the primary application for high polymer is, of course, to resist those load-related distresses, fatigue, cracking, and rutting. There's rutting that can happen in the surface, but there's also rutting that can happen in the base layer, okay? High polymer is effective at addressing both types of rutting. Also addresses top-down cracking, and it's really found a home addressing reflective cracking, okay, from PCC pavements and also cracked asphalt pavements before those cracks reflect through that new surface and imprint onto the new surface. So why are we using it? Again, a big application is with these cracked pavements. Now, what I say about reflection cracking is that it's not a matter of if those cracks are going to reflect back through, it's a matter of when. Whether you're using a bond breaker, some type of grid system, or high polymer, those cracks are eventually going to imprint themselves on the surface. But high polymer has been found to delay that time period by quite a bit compared to some of the alternatives. Now, it's a stiff material, but not a brittle material. And it's found a lot of applications in thin overlays, high-performance thin overlays. Okay, and as you see there, you're able, with those thin overlays, to support the same traffic level at a thinner surface. And I'll talk a little bit more about that. So why are we using it? It's highly elastic. It can be used in almost any mix. Just replace the binder. Now, when we talk about extreme use cases, this is probably one of the most extreme cases I can think of. And before I talk about this slide, I want to talk about a phone call that I received. So I had a manager of the Port of Miami contact the Asphalt Institute, and they said they were dealing with very heavy shipping containers out there, and it was causing severe rutting on their loading docks and just completely damaging the asphalt. And they were calling us to find out if we had any answers or solutions for how they could deal with this. Now, before I built this slide, I was searching for a set of shipping containers that were stacked 6 high, because that's what's happening in Miami. I don't know where this picture's from, but you can see in the background over there, they're maxing out the load of these things and stacking them 6 high. I mean, that is an incredibly extreme loading condition, point load right there underneath those containers. And so when this gentleman called me, he's asking, we've heard that maybe larger aggregates might help with this, and he's going through all the things that he's been discussing with others. I think he spoke with Napa as well. So for me, I was aware of this project, and I recommended to him that he give high polymer a try. Because again, this is one of those cases that if you can't solve the problem with something like high polymer, you're probably looking at a concrete solution. Okay, so this is exactly what happened in the port of Napier, New Zealand. They implemented a high polymer solution, and it really kind of eliminated the issues that they were having with the damage to the asphalt mat. Now, this is the study that I referenced at NCAT going back to 2009. And one of the things that came out of this study was information about the structural layer coefficient. Now, I know not everyone here has a structural design background, but just very quickly, the way that we design pavements from a structural perspective is it starts with a traffic forecast. And that forecast is normally a 20-year, or it could be a 40-year forecast. Or I would say more modern thinking is we're thinking perpetually. So can we actually design a pavement that would never structurally fail, and we can just put overlays on it over time? Okay, but the point is we develop a traffic forecast, and from there we need to determine what structural number do we need to support that traffic level over a given period of time. Now, the structural number is comprised of 2 components. One is a layer coefficient, and the other is a thickness. Okay, so when you combine a layer coefficient and a thickness, you get a structural number that will support a given traffic load. So when you use the high polymer, it's a lot stiffer, it's a lot stronger, so it has a higher layer coefficient. And that was some of the compelling research that came out of here. And you can see the structural number for basically an identical section, a very similar section that just has the different binder. So it's a 3.9 versus a 5.2. And so this kind of leads to this question of, how do you use this information, or how do you take this forward and build new pavements that may be highly modified? And so my colleague Johnny Habouche addressed this in an article for the Asphalt magazine recently, and he titled it kind of a battle of strategies. So if you have a higher layer coefficient, you have that option. Okay, you can build this layer thinner and support the same traffic level, and that means that you can pave more lane miles. Okay, so you can use this technology that way, or you could build it the same thickness, and you might kind of arrive at a perpetual pavement, something that might never fail structurally. So it's an interesting, thought-provoking article that kind of dives into this concept. So another study that was done, conducted by TTI, was around open graded friction course durability. And I know that's something that the state of South Carolina is very familiar with, that these particular mixes have a significant issue with durability. Now, Florida is actually one of the higher performing states for open graded friction course. I think they're getting about 12 years average lifespan. I know states that are not even getting 6 years. So they're actually doing pretty good, but even with 12 years, they're looking to get more. So they did this study. They're already using PG76 minus 22 PMA, and they wanted to compare that to the high polymer binder. And so they did their evaluation using the Cantabro mass loss test, which basically, I'm sure most of you are familiar with it, but just takes an asphalt specimen and places it in a rotating drum, which then causes a certain amount of mass loss. It's not a very scientific test, but as it turns out, this test correlates very strongly to raveling in the field for OGFC mixtures, especially if you're doing that testing on an aged specimen. So our primary focus is on all the way to the right of that graph where it says 10 days at 95C. This is simulating about 5 years of aging. This is the critical time point when we begin to see raveling in open graded friction course. Now in Florida, they have two primary categories of aggregates, both granite and limestone. And you can see that after aging, the limestone doesn't do so well according to this test after aging. So with the high polymer blend, you begin to kind of take away that variable of the aggregate performance. The high polymer versions did significantly better in this test. And in this study, a prediction model was performed to look at the life cycle benefits of this improvement, and it was estimated that it should equate to about 7 to 8 additional years in service. Now, whether or not that would happen, I don't know, but that's pretty significant improvement. Now, the state of Virginia has been somewhat of a hub for research into highly modified asphalts. And you can see here there's various sections on different interstates where they've implemented highly modified binders in an experimental setting. And we're going to focus on this first section. They've got a pretty good system for tracking pavement management data and performance of their sections over time. On this particular slide, we have rut depth and what is their critical condition index. Okay, so you'll notice that it's not shown on this slide, but 60 is kind of their critical condition, which would initiate some type of rehabilitation. In the state of Virginia, that's normally a mill and fill. So you'll notice as these values kind of dive below 60 on that graph on the left, that's when you're seeing a new rehabilitation. So you had the initial, and then you had the SMA was built in 2010. And then they went with a high polymer dense mix in 2016. So really what you're looking at there is just the rate of deterioration. And just by observation, you can see that the high polymer mixture is really resisting deterioration a lot better, even than the SMA, which is itself a very durable and strong mixture. And on the rut depth, it's kind of the same thing. Now, they also measured alligator cracking, which is bottom-up fatigue cracking, as well as reflective cracking. And again, reflective cracking is one of the types of cracking that this technology has really found a home and has really shown success. And you can see that in this data, that the rate in which the reflective cracks are occurring with that SMA compared to the high polymer. Now, I only have data here going through 2020, but again, very encouraging. And as a final step, they kind of tried to convert this to a life-extending benefit. And what you're seeing here is anywhere from 50% to over 100% benefit, depending on the type of distress that you're measuring. With reflective cracking, it's a very substantial increase before they reach their critical point that initiates that rehabilitation. Now, another project was New York City, First Street in New York City. This is a very high traffic area, not necessarily a lot of heavy loads, but this was a big problem for them. They had a lot of utility cuts and the underlying concrete was a real mess. And so in this case, they went with a 1/2 inch high polymer mixture, and that was done in 2012, and this project was featured in TR News in 2019, and has just been a very big success for that particular pavement section. Another example, and this one was featured in the Asphalt Pro, was Oklahoma's I-40. And they're primarily using HP as a rich intermediate layer for rutting resistance. And this project, again, was very successful and actually was awarded a Perpetual Pavement by Conversion Award by the Asphalt Pavement Alliance. And after 10 years, is maintaining an IRI of 50. In Tampa, Florida, they built these sections as an experiment for reflective cracking. And when they measured it after several years, they were seeing a substantial improvement, over 20% total cracking with their standard PG76-22, and less than 2% total cracking with the HP 76E-22. So again, that reflective cracking seems to be delayed significantly by this technology. Now, studded tires are fantastic for gaining additional traction in snow and ice. However, it's not so good for the asphalt pavement. These are known to cause damage, and in this particular project in Alaska, they implemented a high polymer as a potential solution and saw quite a bit of benefit in reducing the distresses that were occurring under that studded tire. Now, the final case study that I want to mention is Utah, and I'm sure some of you have heard about this project. Now, Utah has been implementing high polymer technology going all the way back to 2015. The only difference is what they were originally doing is taking a standard binder and a standard mix design, and they were just directly replacing that standard binder with this highly modified binder, okay? In 2021, they did something different. They designed a mix intentionally with the high polymer binder. And based on some of the information you see in this chart, it was quite an innovative mixture. Any of you that have worked in mix design, there's certain values here that should tell you that you've got a big problem. For example, 1% air voids, that's not normally something that we target. We don't normally target a VFA of 93%. This would normally trigger some concern that this is going to have a rutting issue or a bleeding issue, right? But they tested it in Hamburg before they built the sections in the field. They did very well both at 20 and 40K passes. And the excitement around this project has been kind of amazing. They built all of this in a single 6-inch lift, and of course, saw in the previous presentation that thick lifts are not a new thing for South Carolina. Now, when they built this 6-inch lift, they measured the density both at the top and bottom, and we're getting 96% both in the top and bottom portions of that layer. It was cited that it was a stable and workable mix, and that regular roller equipment and procedures were followed throughout the project, and no issue. So, again, this is still kind of new, but I think this really kind of changes things, in my opinion. It's just so far outside of what we think is necessary to make a successful pavement. So very innovative project there using high polymer. And one thing also that I want to point out is you notice that PG grade isn't that high. Okay, they have a cooler climate in parts of Utah, and if we were to add something above 5% polymer here, with a starting grade of PG64, that end grade would be much higher. Okay, so I think it's part of the innovation that can be taken away from here is starting with a softer grade and ending up with something around PG76, but highly modified. That seems to be an innovative approach that might work in places outside of Utah as well. So this is a slide that was built from experience of the contractors in Virginia who were directly working with highly modified binders. And I thought this information was excellent, so I wanted to bring it here. These last couple of slides that I have are kind of the lessons learned or the takeaways from real-world applications. So on the plant side, these were, again, this is feedback directly from the contractors in the state of Virginia when they were dealing with these products. So temperatures of the high polymer binders must be monitored at the terminal and upon delivery at the plant. So this is really getting into, we know these binders are much stiffer than typical binders that we're dealing with. Okay, we always have to monitor temperatures, of course, but it can be a little bit more of an issue when you're already dealing with a very stiff binder. You lose too much temperature, you might have a big problem. So this was just a note that came from their experiences. I assume that means that they did at some point run into issues with that. Next is the pump-on-pump transfer system as opposed to the mass flow pump system. And my understanding is that this is a common requirement for highly viscous binders that you would want to use a pump-on-pump system. So this is definitely qualifying as a highly viscous binder. So the next point is that the duration of not more than 3 days in storage is recommended. So what that's really saying is that this product only has about a 3-day shelf life. And that's just not very much. So if it were me, that would be definitely something I would want to zero in on. But definitely great information to know. The last point is that they used warm mix technology to try to improve the workability, and I think they had success doing that. On the field side, no changes from routine established practices in terms of surface preparation or paving operations were reported, and to me that's great news. It looks like if you handle some of the things properly at the plant, you're not going to run into too many field issues and you can kind of proceed with normal operations. It's critical to minimize wait time on the job site for loaded trucks to avoid cooling down and stiffening. Again, this is just tying back into the importance of dealing with an already stiff binder and not letting it get too stiff. And the last point is mostly about their mineral filler. I believe they ran into cases where it was getting too high in moisture content, and they were recommending fluffing that material to prevent issues that maybe with the stiffer binder was more of a problem than normal. That's not necessarily specific to high polymer, but something that I think that they were struggling with the high polymer at one point. And this is my last slide, just some general lessons learned and maybe some repeat here. But this is from a broader perspective than just Virginia. So always consulting with the supplier. I think this is very important, understanding that, the next point there, that you got a very short lifespan with this product. Knowing what to do with that product. I mean, when you manufacture a polymer modified asphalt, you make a concentrate and then you let that down with a neat binder. Okay, so you may want to look for opportunities to do that, or maybe the answer is just that you send that product back to the supplier and they do something with it. But having a game plan in place for this product, if it begins to look like it might exceed that 3 days, it stiffens, I believe, much more rapidly than a standard binder. Wax-like products, an example of one of these might be Sasabit. This falls within the warm mix category. And although warm mix additives could be very helpful for these applications, I don't think wax plays very well with the highly modified asphalt, is the feedback that I'm getting. Using a material transfer vehicle, okay, these are in a lot of cases very useful to create a continuous process, quality, smoother matte. I think for this highly modified asphalt is especially the case. And finally, the quality of the high polymer binder after delivery should always be checked according to specifications. And again, I think this kind of ties into that lifespan of the binder. You don't want to receive that binder on day 3 of a 3-day lifespan. So I believe if those properties are starting to creep a little bit higher, you would be able to pick that up with a very quick test. So just kind of a warning there to always check that binder when it's received to make sure that it hasn't overly stiffened at the point that it was received. So that is it. Happy to take any questions from anyone. I think maybe a little bit ahead of schedule here. Any questions at all? Yes, sir. Steve.
I've used a lot of high polymer in Florida, and we've been able to store it for a little longer than 3 days. You buy this stuff, it's super expensive, and you run into a problem, you can't pay, so you leave it in the tank. We've had no problems up to a week, so I don't know if they've done something with the technology, but I guess my question is why is it so much more expensive? Is it the SBS product? Is it the process of milling it at the terminal, or why is it so expensive?
Yeah, that's a good point. I didn't talk a lot about cost, but I have some information. I've seen that maybe on average about a 30% increase in mix price. Is that about what you've seen, or at least? And maybe on an overall project that may be a large project, you might see 10 to 20% increase, and for a smaller project, probably above 20% increase on the overall project. Yeah, I mean, polymer's very expensive, and so it's really a trade-off. Definitely, it's impacting the mix cost. I think to justify it, you have to either be able to probably make the structure thinner, or make it longer lasting, or the last option is that you're just solving a problem that can't be solved any other way. So there's definitely some cost-benefit analysis that has to be done, and when I'm thinking of concerns of using this product, that's definitely one concern, is does it actually have the benefit that's necessary to justify that cost? But I like your point too about the storage time, because I think that, again, this information is coming in more broadly. I'm not sure if your experience has been more with like the 5% or the 7%, or maybe all the above.
Florida spec is what it's meeting, so
yeah.
I don't know what they're making it with.
But I'm not sure either. I know there have been cases where 3 days is kind of the limit, but it's good to know that in some cases, that it can go a little bit longer. Thank you. Thanks, Steve. Yes, sir.
Did you compare the northern and southern states and how long it lasted?
I'm sorry, could you say that?
Compare how long the tubes lasted in the northern and southern states that you were showing?
A lot of this research, unfortunately, is kind of new. I mean, the technology itself hasn't, I don't think, been around long enough to see how long it can actually last. But I think the expectation is that it can last longer than, the comparison, which would be just the standard polymer modified asphalts. In some of the studies that we're seeing, I think it's, you can expect maybe anywhere from 30 to 50% life extension, and if it's 30% more expensive, it becomes a little bit borderline if that justifies the cost. So I don't think we have all the answers on that. For some applications such as reflective cracking, I think it's very easy to justify it because it's, the concern is that you're going to pave over those cracks and you want to delay as long as you can how long before those cracks reflect through. So I think in certain cases it's easy to justify using it. Maybe in other cases it's not quite as easy.
I think that's more north versus south.
Yes, definitely could be. But I'm sorry, I don't have any specific date on that, but great question. Any more?
I got a quick question.
Yes, sir.
How difficult is like your equipment, your transfer machine, your paver, or even your plant, if you get through running it, what's the procedure of cleaning that equipment properly? Because I know if you leave it, if you don't clean it properly, you can break chains the next morning when it's cold, especially with some of this higher modified lining. Is there any way that you have to take more care to clean or keep your equipment free of that material?
Again, I think that's a great question. I think this is going to be related to the temperature issue. I mean, I'm sure if the material cools off, you're probably going to have a big problem. But Steve, you said you got experience. I don't know directly if it's causing any issues with the equipment cleanup or not, but haven't heard of that.
If I could,
Yes, sir.
You don't want to leave it anywhere. You want to clean that paver MTV out at the end of the night.
We've done SMA, we know.
Under drag and all that, because it feels stiff. It's chipping pattern.
So yeah, another good question. Anything else? Yes, sir.
For your interstate, when you're dealing with base and intermediate, with those applications, your typical asphalt, and then just the surface is going to be the high polymer?
It definitely could be. In the state of Oklahoma, they're using the intermediate layer as the high polymer layer. So it really just depends. In New Jersey, I mentioned they've placed 5 million mixed tons of this stuff, and a lot of their applications are for waterproofing bridge decks and for those ultra thin layers on the surface. So the applications definitely vary. I don't think there's any specific location within the pavement structure that you would have to use it, but I think on the surface is probably more common. You don't often see many cases where the most amount of money is being spent on the underlying layers. So I think the surface is definitely the most common application.
And then a follow-up question, if used on the surface, can that final layer be thinner to kind of offset cost?
Yes, it can, and it's based on that structural number that I mentioned. The structural number is a compilation of the entire structure, the subbase, the base, all of the asphalt layers. And when you have a layer that's much stronger than the comparable layer, which would be, say, the PG76 minus 22, that much stronger layer is going to allow that particular layer to be thinner and still support the same traffic level. So, yes. All right, well, if that's it, thank you all. I appreciate the opportunity.